Divider circuits and Kirchhoff's laws. Voltage divider circuits. Let's analyze a simple series circuit determining the voltage drops across individual resistors. From the given values of individual resistances, we can determine a total circuit resistance. Knowing that resistances add in series. From here, we can use Ohm's law IR to determine the total current, which we know will be the same as each resistor current. It should be apparent that the voltage drop across each resistor is proportional to its resistance. Given that the current is the same through all resistors, notice how the voltage across R2 is double that of the voltage across R1. Just as the resistance of R2 is double that of R1. If we were to change the total voltage, we would find this proportionality of voltage drops remains constant. The voltage across R2 is still exactly twice that of R1's drop, despite the fact that the source voltage has changed. The proportionality of voltage drops is strictly a function of resistance values. With a little more observation, it becomes apparent that the voltage drop across each resistor is also a fixed proportion of the supply voltage. The voltage across R1, for example, was 10 volts when the battery supply was 45 volts. When the battery voltage was increased to 180 volts 4 times as much, the voltage drop across R1 also increased by a factor of 4 from 10 to 40 volts. The ratio between R1's voltage drop and total voltage, however, did not change. Likewise, none of the other voltage drop ratios changed with the increased supply voltage either. For this reason, a series circuit is often called a voltage divider for its ability to proportion or divide the total voltage into fractional portions of constant ratio. With a little bit of algebra, we can derive a formula for determining series resistor. Voltage drop given nothing more than total voltage, individual resistance, and total resistance. The ratio of individual resistance to total resistance is the same as the ratio of individual voltage drop to total supply voltage in a voltage divider circuit. This is known as the voltage divider formula, and it is a shortcut method for determining voltage drop in a series circuit without going through the current calculation of Ohm's law. Using this formula, we can reanalyze the example circuit's voltage drops in fewer steps. Voltage dividers find wide application in electric meter circuits, where specific combinations of series resistors are used to divide a voltage into precise proportions as part of a voltage measurement device. One device frequently used as a voltage dividing component is the potentiometer, which is a resistor with a movable element positioned by a manual knob or lever. The movable element, typically called a wiper, makes contact with a resistive strip of material commonly called the slide wire is made of resistive. The wiper contact is the left-facing arrow symbol drawn in the middle. of the vertical resistor element. As it is moved up, it contacts the resistive strip closer to terminal 1 and further away from terminal 2, lowering resistance to terminal 1 and raising resistance to terminal 2. As it is moved down, the opposite effect results. Shown here are internal illustrations of two potentiometer types, rotary and linear. Some linear potentiometers are actuated by straight line motion of a lever or slide button. Others, like the one depicted in the previous illustration, are actuated by a turn screw for fine adjustmentability. The latter units are sometimes referred to as trim pots because they work well for applications requiring a variable resistance to be trimmed to some precise value. It should be noted that not all linear potentiometers have the same terminal assignments as shown in this illustration, with some. The wiper terminal is in the middle, between the two end terminals. The following photograph shows a real rotary potentiometer with exposed wiper and slide wire for easy viewing. The shaft which moves the wiper has been turned almost fully clockwise so that the wiper is nearly touching the left terminal end of the slide wire. Here is the same potentiometer with the wiper shaft moved almost to the full counterclockwise position, so that the wiper is near the other extreme end of travel. If a constant voltage is applied between the outer terminals across the length of the slide wire, the wiper position will tap off a fraction of the applied voltage, measurable between the wiper contact and either of the other two terminals. The fractional value depends entirely on the physical position of the wiper. Just like the fixed voltage divider, the potentiometer's voltage division ratio is strictly a function of resistance and not of the magnitude of applied voltage. In other words, if the potentiometer knob or lever is moved to the 50% exact center position, the voltage dropped between wiper and either outside terminal would be exactly 1/2 of the applied voltage, no matter what that voltage happens to be, or what the end-to-end resistance of the potentiometer is. In other words, a potentiometer functions as a variable voltage divider where the voltage division ratio is set by wiper position. This application of the potentiometer is a very useful means of obtaining a variable voltage from a fixed voltage source such as a battery. If a circuit you're building requires a certain amount of voltage that is less than the value of an available battery's voltage, you may connect the outer terminals of a potentiometer across that battery and dial up whatever voltage you need between the potentiometer wiper and one of the outer terminals for use in your circuit. When used in this manner, the name potentiometer makes perfect sense. They meter control the potential voltage applied across them by creating a variable voltage divider ratio. This use of the three-terminal potentiometer as a variable voltage divider is very popular in circuit design. Shown here are several small potentiometers of the kind commonly used in consumer electronic equipment and by hobbyists and students in constructing circuits. The smaller units on the very left and very right are designed to plug into a solderless breadboard or be soldered into a printed circuit board. The middle units are designed to be mounted on a flat panel with wires soldered to each of the 3 terminals. Here are 3 more potentiometers, more specialized than the set just shown. The large helipot unit is a laboratory potentiometer designed for quick and easy connection to a circuit, the unit in the lower left corner of the photograph is the same type of potentiometer, just without a case or 10-turn counting dial. Both of these potentiometers are precision units, using multi-turn helical track resistance strip and wiper mechanisms for making small adjustments. The unit on the lower right is a panel mount potentiometer, designed for rough surface and industrial applications. Kirchhoff's voltage law. Let's take another look at our example series circuit. This time numbering the points in the circuit for voltage reference. If we were to connect a voltmeter between points 2 and 1, red test led to point 2 and black test led to point 1, the meter would register 45 volts. Typically the sign is not shown, but rather implied, for positive readings in digital meter displays. However, for this lesson the polarity of the voltage reading is very important. When a voltage is specified with a double subscript the characters 21 in the notation E21, it means the voltage at the first point 2 as measured in reference to the second point 1. A voltage specified as it would mean the voltage as indicated by a digital meter, with the red test lead on point C and the black test lead on point D. The voltage at C in reference to D. If we were to take that same voltmeter and measure the voltage drop across each resistor, stepping around the circuit in a clockwise direction with the red test lead of our meter on the point ahead and the black test lead on the point behind, we would obtain the following readings. Kirchhoff's voltage law. Let's take another look at our example series circuit. This time numbering the points in the circuit for voltage reference. If we were to connect a voltmeter between points 2 and 1, red test led to point 2 and black test led to point 1, the meter would register 45 volts. Typically the sign is not shown, but rather implied, for positive readings in digital meter displays. However, for this lesson the polarity of the voltage reading is very important. When a voltage is specified with a double subscript the characters 21 in the notation E21, it means the voltage at the first point 2 as measured in reference to the second point 1. A voltage specified as it would mean the voltage as indicated by a digital meter, with the red test lead on point C and the black test lead on point D. The voltage at C in reference to D. If we were to take that same voltmeter and measure the voltage drop across each resistor, stepping around the circuit in a clockwise direction with the red test lead of our meter on the point ahead and the black test lead on the point behind, we would obtain the following readings. We should already be familiar with the general principle for series circuits stating that individual voltage drops add up to the total applied voltage. But measuring voltage drops in this manner and paying attention to the polarity mathematical sign of the readings reveals another facet of this principle, that the voltages measured as such all add up to 0. This principle is known as Kirchhoff's voltage law, discovered in 1847 by Gustav R. Kirchhoff, a German physicist. And it can be stated as such. The algebraic sum of all voltages in a loop must equal zero. By algebraic, I mean accounting for signs, polarities, as well as magnitudes. By loop, I mean any path traced from one point in a circuit around to other points in that circuit, and finally back to the initial point. In the above example, the loop was formed by following points in this order 1, 2, 3, 4, 1. It doesn't matter which point we start at or which direction we proceed in tracing the loop. The voltage sum will still equal zero. To demonstrate, we can tally up the voltages in loop 3, 2, 1, 4, 3 of the same circuit. This may make more sense if we redraw our example series circuit, so that all components are represented in a straight line. It's still the same series circuit, just with the components arranged in a different form. Notice the polarities of the resistor voltage drops with respect to the battery. The battery's voltage is negative on the left and positive on the right, whereas all the resistor voltage drops are oriented the other way, positive on the left and negative on the right. This is because the resistors are resisting the flow of electrons being pushed by the battery. In other words, the push exerted by the resistors against the flow of electrons must be in a direction opposite the source of electromotive force. Here we see what a digital voltmeter would indicate across each component in this circuit. Black lead on the left and red lead on the right, as laid out in horizontal fashion. If we were to take that same voltmeter and read voltage across combinations of components, starting with only R1 on the left and progressing across the whole string of components, we will see how the voltages add algebraically to zero. If we were to take that same voltmeter and read voltage across combinations of components, starting with only R1 on the left and progressing across the whole string of components, we will see how the voltages add algebraically to zero. The fact that series voltages add up should be no mystery. But we notice that the polarity of these voltages makes a lot of difference in how the figures add. While reading voltage across R1, R1, R2, and R1, R2, R3, I'm using a double dash symbol to represent the series connection between resistors R1, R2, and R3. We see how the voltages measure successively larger, albeit negative magnitudes, because the polarities of the individual voltage drops are in the same orientation. Positive left, negative right. The sum of the voltage drops across R1, R2, and R3 equals 45 volt, which is the same as the battery's output, except that the battery's polarity is opposite that of the resistor voltage drops. Negative left, positive right. So we end up with 0 volts measured across the whole string of components. Kirchhoff's voltage law will work for any circuit configuration at all, not just simple series. Note how it works for this parallel circuit. Being a parallel circuit, the voltage across every resistor is the same as the supply voltage, 6 volts. Tallying up voltages around loop 2345672, we get. Note how I label the final sum voltage as E22, since we began our loop stepping sequence at point 2 and ended at point 2. The algebraic sum of those voltages will be the same as the voltage measured between the same point E22, which of course must be 0. The fact that this circuit is parallel instead of series has nothing to do with the validity of Kirchhoff's voltage law. For that matter, the circuit could be a black box, its component configuration completely hidden from our view, with only a set of exposed terminals. For us to measure voltage between and KVL would still hold true. Try any order of steps from any terminal in the above diagram, stepping around back to the original terminal, and you will find that the algebraic sum of the voltages always equals 0. Furthermore, the loop we trace for KVL doesn't even have to be a real current path in the closed circuit sense of the word. All we have to do to comply with KVL is to begin and end at the same point in the circuit, tallying voltage drops and polarities as we go between the next and the last point. Consider this absurd example, tracing loop 23632 in the same parallel resistor circuit. KVL can be used to determine an unknown voltage in a complex circuit, where all other voltages around a particular loop are known. Take the following complex circuit. To make the problem simpler, I've omitted resistance values and simply given voltage drops across each resistor. The two series circuits share a common wire between them, wire 7, 8, 9, 10. Making voltage measurements between the two circuits possible. If we wanted to determine the voltage between points 4 and 3, we could set up a KVL equation with the voltage between those points as unknown. Stepping around the loop 34983, we write the voltage drop figures as a digital voltmeter would register them, measuring with the red test lead on the point ahead and black test lead on the point behind as we progress around the loop. Therefore, the voltage from point 9 to point 4 is a positive 12 volts because the red lead is on point 9 and the black lead is on point 4. The voltage from point 3 to point 8 is a positive 20 volts because the red lead is on point 3 and the black lead is on point 8. The voltage from point 8 to point 9 is 0. Of course, because those 2 points are electrically common. Our final answer for the voltage from point 4 to point 3 is a negative 32 volt, telling us that point 3 is actually positive with respect to point 4. Precisely what a digital voltmeter would indicate with the red lead on point 4 and the black lead on point 3. In other words, the initial placement of our meter leads in this KVL problem was backwards. Had we generated our KVL equation starting with E34 instead of E43, stepping around the same loop with the opposite meter lead orientation, the final answer would have been E34 32 volts. It is important to realize that neither approach is wrong. In both cases, we arrive at the correct assessment of voltage between the 2 points. 3 and 4.3 is positive with respect to point 4, and the voltage between them is 32 volts. Current divider circuits. Let's analyze a simple parallel circuit determining the branch currents through individual resistors. Knowing that voltages across all components in a parallel circuit are the same, we can fill in our voltage current resistance table with 6 volts across the top row. Using Ohm's law IR, we can calculate each branch current. Knowing that branch currents add up in parallel circuits to equal the total current, we can arrive at total current by summing 6 mA, 2 mA, and 3 mA. The final step, of course, is to figure total resistance. This can be done with Ohm's law I in the total column, or with the parallel resistance formula from individual resistances. Either way, we'll get the same answer. The current through R1 is still exactly twice that of R3, despite the fact that the source voltage has changed. The proportionality between different branch currents is strictly a function of resistance. Also reminiscent of voltage dividers is the fact that branch currents are fixed proportions of the total current, despite the fourfold increase in supply voltage. The ratio between any branch current and the total current remains unchanged. Using the original parallel circuit as an example, we can recalculate the branch currents. Using this formula, if we start by knowing the total current and total resistance, if you take the time to compare the two divider formulae, you'll say that they are remarkably similar. Notice, however, that the ratio in the voltage divider formulas are an individual resistance divided by R total and how the ratio in the current divider formula is R total divided by Rn. It is quite easy to confuse these two equations, getting the resistance ratios backwards. One way to help remember the proper form is to keep in mind that both ratios in the voltage and current divider equations must equal less than 1. After all, these are divider equations, not multiplier equations. If the fraction is upside down, it will provide a ratio greater than 1, which is incorrect. Knowing that total resistance in a series voltage divider circuit is always greater than any of the individual resistances, we know that the fraction for that formula must be Rn over R total. Kirchhoff's current law. Let's take a closer look at that last parallel example circuit. At this point, we know the value of each branch current and of the total current in the circuit. We know that the total current in a parallel circuit must equal the sum of the branch current. But there's more going on in this circuit than just that. Taking a look at the currents at each wire junction point node in the circuit, we should be able to see something else. At each node on the negative rail wire 8765, we have current splitting off the main flow to each successive branch resistor. At each node on the positive rail, we have current merging together to form the main flow from each successive branch resistor. This fact should be fairly obvious if you think of the water pipe circuit analogy, with every branch node acting as a T-fitting, the water flow splitting or merging. with the main piping as it travels from the output of the water pump toward the return reservoir or sump.